The next step is to calculate the probability for a transition between the ground state and the first excited state. This will give us both selection rules that apply to the absorption of infrared light. The first part of this section will be quite general and also apply to the transitions observed in UV visible spectroscopy. I will use the Dirac notation here, where the states are represented by vectors because I find it more illustrative and clear. You might be more familiar with the position representation, where the states are represented by wave functions. The derivation works exactly the same in both forms of the theory. In what follows, do not worry too much about the details of the calculation, but try to get the concepts. To calculate the transition probability, we will use Fermi's golden rule, which was already mentioned in the lecture Introduction to Spectroscopy. According to this rule, the probability for the transition from the initial state psi0 to the final state psi1 is proportional to the squared absolute value of the dot product between the state vector psi1 and the vector produced by the action of the perturbation operator v on the initial state vector psi0. In the position representation, the same probability is given by the squared absolute value of the integral of the product of conjugate complex of wave function psi1, the perturbation potential v, and the initial wave function psi0. In order to proceed, we have to find expressions for the perturbation operator and to think about psi0 and psi1. As we have already seen, the electric field of the electromagnetic wave interacts with the partial charges of the molecule. To simplify things, we describe the distribution of partial charges simply by the dipole moment of the molecule. Then the interaction is between the electric field and the dipole moment. Classically, the interaction energy between a dipole and an electric field is this expression, which is the scalar product between the dipole moment vector and the electric field vector. The lines above the symbols indicate the vector nature of the quantities. By analogy, the interaction energy operator between a molecule and light is given by the same expression, where V and mu are operators that describe our molecule of interest. E is the oscillating electric field vector of the electromagnetic wave. We return now to Fermi's golden rule. The dot product psi1 v psi0 contains two vectors. The vector that is generated by the action of the perturbation vector v on the initial state vector psi0 and the final state vector psi1. The dot product is a projection of these two vectors on each other. It analyzes how similar these two vectors are. The projection is 0 if the two vectors are orthogonal. It is maximal if they have the same direction. If the perturbation v has no influence on psi0, then the perturbation does not change the initial state vector, and v times psi0 equals psi0. The scalar product psi1 v psi0 becomes then the scalar product between psi1 and psi0, which is 0, since both vectors are eigenvectors of the Hamilton operator and therefore orthogonal to each other. Only if the perturbation deforms the initial state psi0 so that it somewhat resembles the final state psi1 will the scalar product psi1 v psi0 and the probability for the transition be different from 0. When we insert this perturbation potential into the expression for the transition probability, we obtain this expression, where we can extract the electric field from the scalar product because it does not act on the eigenstates of the system. Only operators do that. Both the term on the left, this one, and the electric field are vectors. But why is the term on the left a vector? This is because the dipole moment operator has three components, one for each direction in space. So the term in brackets represents actually three scalar products, one for the x direction, one for the y direction, and one for the z direction. In other words, the term in brackets is a vector. So when we evaluate this expression, we have to consider the direction of the vectors and have to multiply their length with the cosine of the angle between them, which I have named alpha. With this, the transition probability becomes proportional to this expression. Thus the scalar product psi1 mu psi0 and its squared absolute value determine the transition probability. They are therefore fundamental quantities in spectroscopy and have been given names: transition dipole moment or transition dipole, and dipole strength or oscillator strength. Both are quantities that entirely depend on the molecule and on the initial and final states. As we have seen in the equation above, this one, the probability for a transition depends also on the angle alpha between the transition dipole moment and the electric field vector. The probability is large when both quantities are parallel or antiparallel, but zero when they are perpendicular. The transition dipole moment between the ground state and the first excited state is often abbreviated μ1, 0. It is written like this in the Dirac notation and like this in the position representation. The most common unit of the transition dipole moment is dBi. It is a unit in the CGS system, and the corresponding unit in the SI system is Coulomb times meter. Here's dBi and here's Coulomb times meter, and the conversion factor is given here for completeness. The transition dipole moment has the same unit as a classical dipole moment. As the classical dipole moment, it is also a vector. Dipole strength, d10, is the squared absolute value of the transition dipole moment. It is proportional to the transition probability and therefore also to the integrated absorption coefficient epsilon, as shown here. The Einstein coefficient A for spontaneous emission and the Einstein coefficient B for induced absorption or emission are also proportional to this quantity. We've met these coefficients already in the lecture Introduction to Spectroscopy. We proceed with analyzing the transition dipole moment, and the next step is to think about the state vectors psi0 and psi1. Psi0 and psi1. When infrared light is absorbed, only the nuclei change their vibrational state from state N to state M. The electrons remain in their ground state. When we now use the Born-Oppenheimer approximation, we can write the state vectors psi0 and psi1 as products of the state vectors of the electrons and of the nuclei. Psi0 is the product of the electronic ground state vector with a nuclear state vector for state N. Psi1 is the product of, again, the electronic ground state vector with the nuclear state vector for state M. The Born-Oppenheimer approximation is possible because the nuclei are much heavier than the electrons and therefore move much slower. It assumes that the movement of the nuclei does not depend on the movement of the electrons. Instead, the electrons adapt instantaneously to the position of the nuclei. One consequence of the Born-Oppenheimer approximation is that the vibrational energy levels are calculated without considering the vibrational kinetic energy of the electrons. The vibrational energy levels correspond therefore to the movement of the nuclei only. This is different from the classical view, where we have said that the moving masses are the atoms, meaning the nuclei plus those electrons that faithfully follow the movement of the nuclei. However, the contribution of the electrons to the vibrational energy will be very small because of their small mass. So when it comes to the question, what are the moving masses in vibrational spectroscopy, you can answer either the nuclei or the atoms, and I will consider both answers as correct. The transition dipole moment for a transition from the vibrational level n to level m of the electronic ground state can be written as given here, where I have just inserted the product expressions for the initial state psi 0, turning to this, and the final state psi 1, here and there. This is the same transition dipole moment that is relevant for the absorption of UV vis light. The only difference is that the electrons are in their ground state also after the transition. We continue by evaluating the expression for the transition dipole moment. We started with Fermi's golden rule and used the Born-Oppenheimer approximation to write the state vectors as products of an electronic state vector and a nuclear state vector, as shown here. Further calculation shows that this transition dipole moment is 0 when it is evaluated at fixed positions of the nuclei. But when we consider that the dipole moment operator changes when the nuclear positions change, the result is different from 0. Then the transition dipole moment can be factored into two terms that give rise to two selection rules of infrared spectroscopy. The right-hand term gives rise to the selection rule that vibrational transitions only occur to the next vibrational level, delta n equals plus minus 1. This selection rule is strictly valid only for the harmonic oscillator. This selection rule limits the number of transitions that are relevant for infrared spectroscopy considerably. In the mid-infrared spectral range and at room temperature, we have to consider only the transition from the vibrational ground state to the first excited state, because the large majority of oscillators are in the vibrational ground state before absorption. The reason for this is that the thermal energy is smaller than the energy gap to the first excited state. For such a transition from the vibrational ground state to the first excited state, the transition dipole moment has finally this expression here. The term on the right-hand side is calculated only from the nuclear state vectors or wave functions. It is a factor that depends on the reduced mass of the oscillator here and its frequency here. It has different values for different vibrational transitions. In particular, it is 0 when delta n is different from plus minus 1. Therefore, it is responsible for the selection rule delta n equals plus minus 1, as mentioned before. The term on the left-hand side has contributions from electrons and nuclei. It is the expectation value of the change of the dipole moment when the oscillation passes through the equilibrium positions of the nuclei, which are here denoted by R0. For a simple stretching vibration, this term is just the change of dipole moment when the oscillator passes through the equilibrium bond length L0. This term gives rise to the selection rule that infrared absorption only takes place when the dipole moment of the molecule changes with the vibration. The larger the change, the stronger the absorption. Often a large change is correlated with a large bond polarity, which means a large difference in the electronegativities of the bonded atoms. This is the same conclusion that we obtained with the classical view. I want to note here that the transition dipole moment for infrared spectroscopy has a simple classical analogon, which is simply the change of dipole moment when the vibration passes through the equilibrium structure. This is different from the absorption in the ultraviolet and visible spectral range, where the transition dipole moment has no such classical analogon.